address in today's video is the very basics and the foundation of building physics. And building physics kind of always circles around air and heat and water. It's these kind of topics that are very, very important when it comes to detailing and designing the constructions. So when you go back, and we'll have to zoom out a little bit in time here and think about the purpose of architecture. There's a very social function behind it. On the one hand, it used to be that kind of gathering place. It's marking that spot within the landscape. It's that one location that you call home with your family or your extended tribe. And then, of course, there's a much more practical purpose for architecture as well. And back in the day, it would be protection from enemies or wild animals. You want to make sure that you are protected and safe, especially at nighttime. You don't want anyone to sneak up behind you. And then more commonly, it would be protection from the elements such as rain, wind, sun, so the weather in general. And of course, if we now think about us modern human beings, we don't necessarily need to have these kind of protections or functions, but what we want now is comfort. And comfort for us means having a controlled interior climate. Because as human beings, we're actually quite fragile and we're relatively vulnerable. And there's only a very small band or difference in temperature that we feel actually really comfortable in without being too cold or without being too hot. And of course, that's a really broad explanation as well. As you would probably know, it's very individual on how comfort is perceived, but that's probably a whole other topic here. But the idea of introducing that controlled climate has actually caused a little bit of a problem, so to speak, in our detailing of our exterior walls, because all of a sudden we don't just want, or we don't just need a simple wall that is giving us shelter, that's protecting us, but all of a sudden we have these kind of sandwich-like constructions that use multiple different materials where we have to be really crucial in how they are being assembled together. Because actually the idea or the demand for having a controlled temperature on the inside and therefore introducing insulation within our construction has an implication on how not just heat is transmitted through these walls, but therefore is also affecting how vapor is transmitted through these constructions. And we will have a look at this in another video on how moisture control works. But because there's a heat transmission happening, it also means that there's vapor flowing through the construction, and you have to be really, really careful in how that's being assembled. Because constructing details, it's all about, at the end of the day, it's all about protecting your construction from water, from any type of water, whether that's vapor or it's in liquid form, because that's what eventually causing damage within your construction if you're not in control of that water, or it is at best it is causing problems within your insulation by making insulation inefficient because it's getting damp, so it doesn't have the same properties anymore. So yes, unfortunately that demand for a controlled climate has made things a little bit more difficult. So when we have a look at heat transmission, and again that controlled climate on the inside of a building, what will happen in wintertime is that because warm air travels into the direction of cold air, because heat in physics, there's no such thing as coldness in physics, it's the absence of heat. So the warm air on the inside and the cold air on the outside, if they are not separated from each other, they will try to balance each other out, and they will try to find an equilibrium. So therefore the hot air is traveling into the direction of cold air. And we will have the same thing in summertime as well. We have the slightly hotter air on the outside that is now all of a sudden starting to mix with the slightly colder air on the inside, which we deem to be comfortable. And what we want to do, of course, is stop these heat transmissions from happening so that we can have that comfortable climate on the inside. But unfortunately, we can't completely stop these heat transmissions because no material is completely insulating that, or it wouldn't be practical for us anyways because we want to breathe and we need fresh air as well. But what we can do is that we can slow down these heat transmissions. And how do we do that? By increasing the performance, the thermal performance of our building's envelope, and most often that's through introducing materials that provide insulating qualities, and of course having insulation in the first place. So looking at heat flux in building physics, we express heat flux using the letter Q as indicated on that arrow in this construction. And it's being calculated by theta SE, which is the temperature on the outside surface, minus theta SI, which is the temperature on the inside, divided by R. And R in this case is the resistance of the material where the heat flux is traveling through. The resistance, I've kind of indicated it here, is something that again is slowing down that heat flux, and it's similar like in electrodynamics in physics as well. So the resistance is relative to the thickness of a material, expressed as S here, and the material thermal conductivity coefficient. Sometimes sometimes it's called K, sometimes it's called lambda, the Greek letter for L as well. Both of these will usually indicate the same value. And lambda or K, if you have a specific material, a specific manufacturer, you might find the information about that thermal conductivity coefficient from that manufacturer, because usually that's a value that's determined in a lab condition, and they can tell you that value quite precisely. Sometimes you would also find an indicative value. You can simply Google it and you would find a very close enough value for that material. For instance, in this case, common brick has a value, a lambda value of roughly 0.8 watt per meter Kelvin. So again, or importantly here, we are expressing, or we are using Kelvin in physics. It's a standard unit that's being used. So R, again, the resistance is S, material thickness, divided by the material thermal conductivity coefficient. There's actually a graphical way in how you can express the development of that thermal conductivity within your construction by having a temperature scale on the inside and on the outside, and you can show how that is actually transmitting through that material in a graphical way. And then that actually becomes really helpful in comparing two materials as well. So on the left hand side we have brick, again has a lambda value of roughly 0.8 watt per meter Kelvin, and on the right hand side we have timber, the same thickness of the material but having a different lambda value, and that one here is 0.15 watt per meter Kelvin. And of course, because K or lambda is on the bottom of the fraction, therefore meaning that a lower K or lambda value is actually increasing the resistance, therefore increasing the insulation properties of that material. And as you can see in the graphical representation as well, is that timber is actually slowing down that heat flux. The line is flatter than in the brick. So that sort of indicates that timber is a better insulator than a common brick material. And of course, coming back to that idea of having multiple materials in within a construction, that means that we have to calculate that heat flux for every single layer, and we can add them up. Of course, every layer has a different thickness, and every material has a different thermal conductivity coefficient as well. So we can actually calculate each of those layers individually And then in this graphical representation, actually, we can show that as well. In this kind of example as well, most importantly, we will see that the insulation that is within that kind of common timber construction has the biggest impact on the heat transmission, actually slowing down that heat transmission as well. Yes, I hope this is helpful in understanding how what kind of factors contribute to heat transmission within a construction, and just to get a basic idea of how every single material is actually contributing to that in some way. We'll have a closer look at about vapor transmission as well in a different video. And if you have any questions or any other requests on specific videos and information that you would like to see, just let me know and I'll be happy to answer those for you.